Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi everyone, I'm very pleased to introduce Ankan Saha, who's here visiting us this summer from the University of Chicago. He's been doing some cool internship work with Zilla, working on predictive web search now, but today he's going to talk about the usual work he's doing for his PhD on optimization and I guess some Nesterov method stuff. So looking forward to an interesting talk.
Thanks. Thanks for the introduction, Sumit. So this has been stuff that I've been doing for like the last 2 years or so. And we've been using some smoothing techniques to basically optimize risk measures and look at various applications in machine learning where this is applicable. So at the heart of most machine learning problems, you will see a regularized minimization problem. And more often than not, this generally results in an optimization problem, which is becoming increasingly larger in size. So just to give you a few examples, in the Hadron Collider, you'll have huge amounts of data, gigantic data sets of incredibly large dimensions. If you look at the field of the internet, websites like Google, Facebook, Twitter, they are collecting gigantic amounts of data these days. And more often than not, these can often be very skewed data sets with very large dimensions and maybe very few data points, whereas the converse can also be true, and it's often true actually. In MRI images, as well as in most medical imaging problems, you will actually come across the large P small n domain, where basically the data is very large dimensional, but you don't get that many data points. So with this deluge of big data, it is very important to come up with efficient optimization schemes, which are also faster. And more importantly, you want to come up with optimization methods which are suited to the specific problem and can give you faster rates of convergence or faster performance in real life. So what we do in our work is we incorporate this new style of smoothing in various non-smooth objectives. I'll define all these terms as I go along. So what we do is basically we give faster rates of convergence on a large number of existing machine learning problems. And to give you a few examples, our methods are applicable to simple binary SVMs, structured max margin prediction, problems of finding minimum enclosing shapes, and something that I'll be talking in detail is efficient smoothing of multivariate scores. So problems like minimizing the ROC score or the precision recall break-even point, and so on. So before I go into the details, I'll give you a crash course of 1 or 2 slides on basically the convex analysis that I need for this talk. So as most of you will be aware, a convex function can be lower bounded by a linear approximation. So in our talk, we'll mostly be concerned with a few classes of convex functions. Our universe will mostly consist of Lipschitz continuous functions. So basically, the function value is bounded by some constant times the actual distance of the points. So basically, the closer points will be closer in terms of function value as well. Another particular class of functions that we'll be specifically interested in are strongly convex functions. So these are functions that are actually lower bounded by a quadratic rather than the simple linear functions that the convex functions are lower bounded by. So you can think of any standard quadratic function as a strongly convex function, as an example of a strongly convex function. But in particular, the definition is that instead of just the linear approximation, you now have a quadratic term in the lower bound as well. So to just form an analog, the analog is the class of functions which are upper bounded by such a quadratic approximation. And these are what we call the functions which these are exactly the functions which actually have Lipschitz continuous gradient, and they're also known in the machine learning literature as smooth functions. So these are 2 particularly well-behaved function classes for which there are much better rates of convergence known in the optimization literature, and that's what we'll be looking at. So to give you an example, this on the left-hand side is an example of a Lipschitz continuous gradient function. So this is the original function, and at any point, you can actually draw a quadratic which will upper bound the function. Similarly, for a strongly convex function, if you take the original function, you can always form a quadratic which will lower bound the function. And then you can actually optimize that particular quadratic function to give better rates of convergence. So that corresponds to this figure. And to just give you an idea, so this is the universe of Lipschitz continuum functions that we're looking at. And you can consider two classes of functions, the strongly convex functions and the smooth functions. And there will, of course, be functions in the intermediate regime, which can be optimized much better. So I'll give you some idea of the state-of-the-art rates. For standard Lipschitz continuous functions, mirror descent methods have already been existing for the last 20 years or so. And they give you order 1 by epsilon square rates of convergence to give, basically to go to an epsilon optimal solution, you would require order 1 by epsilon square iterations. For strong,
I don't understand the concept, sorry. So when you say epsilon, it's within epsilon in x, not in the f value.
No, within epsilon of the f value. So this is actually not epsilon close to the optimal iterate, but epsilon close to the function value. Yeah, whatever all the epsilon optimum things that I'll talk about is in terms of function value. So in terms of basically for strongly convex functions, if you have both strongly convex as well as smooth function results, then you can show that simple projected gradient descent methods can actually converge in order log 1 by epsilon time. Whereas for general smooth functions, there have been these momentum-based methods that have been pioneered by Nesterov for the last almost 30 years now, that actually give you order 1 by square root epsilon rates of convergence. But a lot of machine learning objectives are actually non-smooth. And therefore, it remains a challenge as to how to apply some of these rates into the machine learning problems in an effective way. So I'll show you that how we can, so these are generally black box rates. So you'll say, okay, if a function is strongly convex, you can get this rates of convergence. But yeah.
For the second bullet, you assume strong convexity and...
Yeah, sorry. The second bullet assumes both strong convex. So basically a well-defined condition number. Yeah, so what you want is basically that if you have particular structure defined in your problems, you can actually get better rates of convergence than what might exist for the black box case. So that is what we will exploit in our various problems that we look at. So this is the structure that I'm actually talking about. So suppose you want to minimize a non-differentiable objective which looks as this form. It is the sum of a strongly convex function f and the dual of a smooth function g. So I'll use the term function with Lipschitz continuous gradient and smooth function as, they basically mean the same thing, so I'll use them alternatively. So this objective is actually the sum of a strongly convex function and the dual of a smooth function. So to ease it out, I'll give you various examples. So most regularized risk minimization objectives that you see in machine learning can actually be expressed in this form. In particular, think of, say, the standard SVM objective. This is your L2 regularizer, which is L2 regularizer square, which is a strongly convex term. And the hinge loss can actually be expressed as in this form. And I'll show you in one of the later slides how it can be expressed. So most regularized risk objectives that you actually see, they can be expressed in this form. And the dual can actually be written out like a max term. So if you have an objective in this form, you can come up with, I'll show you how you can actually smooth it to come up with better rates of convergence than what exists in the literature. So if you look at this particular objective, you will see that this argmax might not be unique. And that actually results in this function being non-differentiable and causes problems in differentiating this objective and getting a well-defined gradient and so on. So the key difficulty, as I mentioned, is because of the non-differentiability of the dual function g star. And here, I was trying to minimize with respect to w. What you can do is basically push this max over the variables u outside and push the min over the w inside to get what would be the dual, basically the dual objective. And that actually looks like this. And it is interesting to note that if you have such a well-defined primal objective, the dual over here is smooth. So basically, this dual is differentiable. And so basically, it has a Lipschitz continuous gradient. And throughout the talk, W will refer to the set of primal variables, so basically the primal objective, whereas U will refer to the set of dual variables, which is what I have represented here. So this is how the problem geometrically looks like. You have this function j that you want to minimize. It is non-smooth, so it has all these kinks. And there is this smooth function d, which is its dual, and you want to find out this optimum. Now, convex duality simply gives you that this primal will always lie above the dual. And so you are trying to get to this red star point. Now, one of the ways of smoothing this, of basically optimizing this primal is to come up with a smooth surrogate of it. And you can smooth the primal in several different ways. I'll give you one particular example that actually leads to faster rates in convergence. So the idea is you want to add a strongly convex function in the dual space capital D. So what I do over here is previously you had this objective where you had a maximum over this part. Now I subtract out a strongly convex function in this space. So the idea is if you subtract a strongly convex function, now your argmax becomes uniquely defined. And once your argmax is uniquely defined, you can take gradients. So this function j mu now is a smooth function. And you can control how much strong convexity you are adding by this parameter mu. And if you send mu to 0, basically you're getting to the actual objective j. Yep.
I'm sorry, I'm just trying to follow your logic here. Yep. So I thought you just said that you have the primal problem is difficult, but the dual, solve the dual, you find the same. So you can solve the primal by solving the dual, and the dual is smooth.
No, the dual is smooth, but
why are you now smoothing the primal?
So I want to solve the entire thing in the primal itself. I don't want to solve the optimization problem in the dual.
Why not?
There are two reasons for this. One is that if I solve the dual, I will give you an iterative method to converge to the optimum of the dual. But that inherently does not give you a rate of how fast you're going to the primal optimum. So there is a lot of iterations where you would say, there is a lot of algorithms where you would say, I'm going at order 1 by epsilon rate close to the dual optimum. But suppose I give you an intermediate iterate corresponding to any particular dual iterate. So suppose you have an alpha k. Corresponding to that, I give you a wk, which is in the primal. This has no guarantee of how close wk is actually to w star, or even how close the primal j of wk is to j of w star. Whereas what I will end up bounding is the duality gap. So I'll end up bounding the primal at the primal iterate from the dual at the dual iterate. So the distance from the optimum is sandwiched in between. So of course you'll be going to the optimum in that case.
But this is just because you have a specific preference towards these iterative methods that only get close. I mean, if you would really solve the dual, you'd be done, right?
I mean, I don't know of theoretical bounds whether actually they can give you. So suppose I say that, okay, I get a particular alpha k such that d of alpha k minus d of alpha star minus d of alpha k is less than or equal to epsilon. I don't know how to translate that to a bound from j of wk to j of w star. And I mean, that is what is often done in practice, and it tends to give good results in practice. But I don't know of any any theoretical bounds correspondingly. Whereas if you smooth the primal, I can show you that what you end up getting is a nicely sandwiched bound between the primal and the dual. Yep. So this kind of defines a smooth approximation to it. So this is how the entire thing looks to you. You have this non-smooth primal j of w. What I just showed you is I'm subtracting out a non-negative strongly convex function, small d, which is also bounded by a script d. So what we had here is that small d is non-negative and it's bounded by a script d. So what we're getting over here is that j of mu will always lie below j of w. And if you add mu times the upper bound to small d over here, it will always form an upper bound to the original function. So what we end up getting is we're creating a smooth envelope to our non-smooth function. And pardon?
D is strongly convex?
Yes, small d is strongly convex.
How can it be bounded if it's lower bounded by parabola?
There's a Q2 here. It has to be a bounded set.
It has to be a
bounded
bounded
set.
set. Yeah, sorry. So there is a Q2 over here. So basically, I forgot to mention that. Yeah, we're working in a bounded domain on the dual space, basically. Which is often for example, if you look at SVMs, the dual space is basically a box. Or, for most machine learning problems that I know of, the dual is generally bounded, or a simplex or something like that. So you end up getting an upper bound as well. So the idea is as you basically optimize this smooth function j of mu, and try to send mu to 0 at the same time, you will end up optimizing the non-smooth objective. So your rates will actually depend upon as a trade-off between how well you're optimizing j of mu and how well you're sending mu to 0. So The duality gap now is basically just the value of the primal to the dual, so the difference between the two, and this can be upper bounded by this quantity, just because G of WK is upper bounded by this term. And now, if you can basically say, okay, these are two smooth functions, I have a handle on this. So basically say, suppose I bound this by epsilon by 2, and I choose mu k such that this term is less than or equal to epsilon by 2, then the entire thing is less than or equal to epsilon. And that is basically the entire trick behind the smoothing techniques. And what Nesterov's accelerated gradient methods do are basically they try to optimize this smooth objective G of mu in order 1 by square root epsilon iterations. And what we found out in the course of experiments is that if you actually smooth out the objective in this way and solve the problem in the primal, you can actually throw state-of-the-art very fast solvers. So what in our experiments we actually threw LBFGS at the problem after smoothing it, and it turns out it performs amazingly fast compared to existing state-of-the-art methods that were there. So I'll show you slides for that as well.
So use the second order method.
No, we basically smoothed it out. Then we tried various ways of optimizing this smooth objective. We tried Nesterov's original algorithm as well. We tried CVX opt as well. We tried LBFGS as well. And we saw that basically all the advantages of fast solvers are actually captured by this smooth objective. So to go into some applications, I'll basically talk about smoothing of multivariate measures. In particular, I'll just talk about ROC area today. So the idea is you have all these measures like ROC area and precision recall break-even point, which are kind of very important in areas like natural language processing, speech recognition, sometimes even vision, where especially in the cases where the number of labels, the label classes are very skewed. So suppose you have a very large amount of positive labels as compared to negative labels, it does not always make sense to capture accuracy. So people often try to capture ROC area and so on. And one of the problems with these kind of complicated measures is that they generally combine measures over the entire data set. And so more often than not, they are not individually additive over individual data points. So they are not like a hinge loss that you'll calculate it over individual data point. So more often than not, it's very difficult to apply online learning algorithms to it. So this is kind of a misleading statement. You can actually use online learning algorithms if you define measures over pairs of data points for ROC score area. But I'm right now talking about individual data points. And pardon?
You can transform the problem in a problem with constraint, like an Minimization problem, and use online by having actually the opposite.
You can use
another point.
One way I know of doing it is basically if you consider xi comma xj pairs, where xi is a positive point and xj is a negative point, and
on something like AUC.
Yeah.
It's not going to work well if AUC limited to the top, but you can still do that by looking at defining the problem as a Niemann person.
Okay.
And using a constraint.
Okay.
So I think you can do it by stochastic gradient as well. So
that
you shouldn't say it that way.
Probably that was one of the reasons. Like a lot of people were initially asking us, well, how do you justify your methods given the fact that there are a lot of very fast stochastic gradient descent methods around right now. So
convex if you do it by Niemann person.
Okay.
You can do a stochastic gradient with Niemann person, but the objective is non-convex.
So you basically end up going to a local minima in that case.
Works.
No,
you can do that already.
Alright, so to go ahead with that, I'll just explain briefly what ROC score looks at. So the idea is you define these concept of misclassified pairs. So misclassified pair is a pair ij such that the score that your model gives to xi and xj is reversed to what the actual labels of yi and yj are. So suppose yj is a negatively labeled point and yi is a positively labeled point, but your model is actually giving lower score to xi as compared to xj. So the ROC area is basically defined as 1 minus the fraction of such misclassified pairs. So here script p is basically the number of positive points, and script n is basically the class of positive points and the class of negative points. And Thorsten Jochims had a very famous paper which was looking at max margin formulation for optimizing such multivariate scores. And what he did was he defined measures in a product space, so basically the product space of xi's and xj's. So the idea was you introduce these auxiliary variables z in this product space, and what you do is you define a margin-based empirical risk. So what this empirical risk is basically capturing is very simple. You want your score corresponding to, so I will always will be an enumerator over the positively labeled points, and j will be an enumerator over the negatively labeled points. What you want is that your score over the positively labeled points should be greater than the score over the negatively labeled points by some margin delta. So for the particular case, the margin is just 1. So if that is not the case, so if you incur a loss, you want to punish. So you are having these auxiliary variables z in which are binary variables in 0, 1 to the m. And if this term is actually positive, then your zij will actually be 1. Whereas in the other case, your zij will be 0. So if you incur a loss, your zij will be 1. And if you don't incur a loss, your zij will be 0. So this is just trying to capture what the loss is. And then you will be minimizing over the particular model that you have. So the goal is basically to find an epsilon accurate solution of such an empirical risk. You can add a regularizer to that, and you try to optimize it over the data set. And the state-of-the-art algorithms that existed before were due to general cutting plane methods. So something like bundle risk methods for regularized minimization. They used to solve this. Problem in order 1 by lambda epsilon time for convergence, where lambda is basically the regularization parameter. And so, if you're wondering, SVM perf is exactly a cutting plane method, which is often considered the state of the art for optimizing this. What we get is that our smoothing techniques help us get order 1 by square root lambda epsilon rates of convergence for this same objective, and we show that we are faster in practice as well. So we write down this empirical loss as a maximum over these binary variables in the m-dimensional space. And we note that this is actually equivalent to optimizing over fractional variables beta, which belong to the entire space 0, 1 to the m. And you replace this zij's by the beta ij's over here. And then we see that if you look at the entire regularized objective, where this omega can be 2 norm squared or something like that, this term can now be written in the form that we wanted it to be. So we can actually write it in the as a sum of a strongly convex function f, which is just our regularizer, and this empirical risk can now be written as the dual of a smooth function, where the dual is actually as simple as this. The dual is basically, this is just some convex analysis. The dual can be written as an average sum over the dual variables when they lie in the interval -1 to 1, and they are infinity otherwise. And this nice transform comes out that this A is basically a transform on the primal variables. It is actually just a matrix such that the ijth column refers to this difference between xi and xj. So after we observe this, we basically just apply Nesterov's accelerated gradient scheme and use mu is equal to epsilon by d. So note that mu is actually the rate at which we decrease our strongly convex content in the dual is dependent upon epsilon. So that actually results, that is how epsilon affects our solution. So I won't go into the details of the accelerated gradient scheme of Nesterov, but what I want to say is that it is analogous to gradient descent methods, but what you do is you don't take the gradient of the previous iterate. Rather, what you take is you take the gradient at some kind of a combination of the last 2 iterates. So you can think of it as, so that is what is often mentioned, what is often referred to as momentum-based methods in the optimization literature. So you take some kind of affine combination of the last 2 iterates and take the gradient of the function at that point. And it is the first order method, and it is shown to be convergent in this rate, these many iterations, where script d is basically the upper bound on the strongly convex function that we use, and norm of A is basically the norm of just this matrix A that I was talking about. So it is interesting to note that if you just throw any smoothing function to it, you will screw up this contribution that you have. This script d times norm of A it is not necessarily a constant. It is not independent of the kind of smoothing you use. In particular, if we had smooth without, so basically in our smoothing, we had actually used this contribution xi minus xj. So our beta ij nicely couples up over the pairs of positive and negative points. Whereas we could have introduce individual variables for the primal points and individual variables for the negative points. Turns out if you do something like that, this component ends up becoming dependent on the number of data points. So you will actually end up incurring more dependence on the number of data points than what we get. So basically, in our case, script d times norm of a is actually a constant. So our number of iterations is actually completely independent of the number of data points. Whatever dependence on the number of data points we get is basically due to gradient calculation at every iteration. And so it turns out that the smoothing needs to be done in a pretty non-intuitive way, and you cannot just say that, okay, we can throw any particular smoothing at it. So to give you some intuition about how we look at the gradient evaluations, so the gradient since it is a first order method, it will of course go via calculating gradient at every step. And the gradient at every step looks like this very complicated form. What it is doing is basically, it is summing over pairs, over all the positive points, and inside that sum, there is another sum of the negative points. And these alpha hat ij's are actually medians of 1, 0, and this complicated term, where aj comes from the negative points and ai comes from the positive points. And this basically comes up if you look at how to optimize SVM perf as well. So basically it is a standard gradient descent scheme that comes up in optimizing ROC score in general. So if you actually try to calculate this gradient naively, what you see is that you might end up getting order n squared dependence, because you're summing up over all the positive points and summing up individually over all the negative points. And you have to do the same thing over here as well. So if you try to calculate the gradients naively, you end up getting order n squared dependence. So there was this famous algorithm by Thorsten himself, which we actually see that it applies in our case as well. What they end up doing is basically it ends up calculating this gradient in order n log n time. So the idea is you sort these terms aj's and ai's in terms of in an increasing order, and then you basically calculate this internal sums in linear time. So that is a pretty simple bookkeeping algorithm which sorts these particular aj's and ai's, and you can see that it is very easy to keep track of them so that you can calculate these individual sums in order n time once you've sorted them. So basically the entire complexity is due to the sorting algorithm, which gives you order n log n dependence to calculate the gradient. Yeah.
If you were to subsample positives and negatives, would you end up with pretty bad concentration, or what's the reason?
So theoretically you can subsample, but depending upon the amount of skewness in the labels that you have, it can be a pretty bad estimate.
So can you subsample in a weighted way from basically take all positives and take a subsample of negatives if it's negative, and then properly rescale?
We tried simple rescaling methods, but that were not working well. And especially we tried doing experiments on the DNA dataset, which is actually a pretty skewed one. And in that case, the results were not that good if you were trying to calculate this naively.
You didn't consider any guarantee of, if you subsample, you obviously are solving the same problem, but you're not far from the true problem, which means that this gain could be better than the gain of changing the objective.
Yeah, we did not consider.
I'm just wondering, empirically, if you were to subsample, how tightly would the gradient converge to the truth from the sample? I don't know. It's an experimental question, so.
If you subsample each iteration,
So you have an independent subsampling before every iteration, or you just subsample in the beginning?
You just pick a sample, you just draw a sample instead of taking it for full n log n. Or
then because it's a stochastic problem, you cannot address it with the standard optimization process anymore. Yeah. Because the problem changes at every step.
So you end up,
or you can see optimization with noisy gradients, which is against stochastic approximation.
So this is the gradients method that I was talking about. So you end up getting an order n log n complexity per iteration for calculating the gradients. And interestingly, the same bookkeeping method actually allows you to calculate the smooth function value as well at every iteration. So the entire complexity per iteration turns out to be order n log n. And I just included this slide to show you the variety of the data sets that we were looking at. In particular, this DNA is a monster data set. Oh no, sorry, this one, the DNA string. It is a monster data set, and it has a very, very skewed ratio. And there are some other very large data sets that we looked at as well. In particular, KDDB was really large, and OCR was pretty large as well. So what we did was we compared with the standard cutting plane algorithms, in particular bundle methods for regularized minimization, and we tried various possible standard algorithms after smoothing, but in particular the results that I'll show you is with applying LBFGS after you smooth algorithms. And we basically calculated our smooth loss and gradient evaluation using PETC and tau libraries from Argonne National Labs, and that helps in faster matrix vector multiplication and stuff like that. So these are some of the curves that we have. I mean, the blue curve corresponds to our algorithm, and the red curve corresponds to bundle methods. And you can clearly see that both the top curves correspond to basically how fast the regularized risk is decreasing, and this corresponds to the generalization performance. So you can see in terms of both, the blue curve is way ahead of the red curve in terms of convergence. And we actually use like 80% of the data for training and 20% for testing. So the generalization performance is pretty, significantly better than bundle methods as well. So yeah, so that's mostly about the ROC area problem. In the remaining of the talk, I'll try to show you how this particular smoothing technique can be applied to various other problems in. Yep. Do you have?
Well, you said you compare with LBFGS. It's not even.
No, we don't. We actually smooth the objective and run LBFGS as our optimization algorithm.
Okay.
Yeah. So
the blue is run.
Yeah, the blue is basically LBFGS after applying smoothing. Nesterov style smoothing.
Did you try Nesterov's first?
Yeah, Nesterov, we tried that, but that was not as fast as LBFGS. But it was still faster than the red line. It was still faster than the existing other cutting plane methods in general. Which is kind of surprising because in various real-life experiments, the bundle methods actually attain curves which are closer to order log 1 by epsilon as compared to order 1 by epsilon. So their theoretical upper bound is order 1 by epsilon, but they're often, in most data sets, their performance is actually pretty close to order log 1 by epsilon. Which actually, initially Vichy was conjecturing that probably it is a weakness in their bounds, but then we ended up showing lower bounds for bundle methods as well. So that makes me wonder whether this is an artifact. There is some kind of weakness in terms of smooth analysis or something like that. Like these order 1 by square root epsilon rates are optimum in terms of first order methods. That has been theoretically shown by Nemirovsky. But in many real life data sets, they actually perform amazingly better compared to order 1 by square root epsilon. So if you look at the curve, it is often as close to log 1 by epsilon. So, I don't know whether it's an artifact of, whether there is any stronger analysis, amortized analysis.
Category of optimization problems are not well chosen.
Yeah. It's just the upper bound.
Yeah.
You have solved the particular problem. So it's upper bound for the whole general thing.
Yeah. But then, of course, the lower bound is also for specific problems that we handpick and find and say that, okay, these are the lower bounds. Of course, so in general cases, it might be better. Yeah, so I'll talk about one other problem that we solved, a problem that on the surface looks completely different. So this is the problem of finding minimum enclosing convex shapes, in particular the minimum enclosing ball problem. So the problem is very simple. You have been given n points in d-dimensional space, and you want to find the smallest ball which encloses all of these points. And this has a large amount of implications in data mining, machine learning, even statistics, and I was surprised to see that, I reached this problem by looking at SVM solvers. So there's something called ball convex machine, core vector machine or ball vector machine, which came out around 2007. It was considered to be a very fast SVM solver. And what it did was basically solve the dual of the minimum enclosing ball problem. And the previous best algorithms for this are from the computational geometry community, and they have this scheme called finding the core sets, which is like I won't go into the details of that. That is a pretty constructive approximation scheme that gives you 1 plus epsilon multiplicative approximation guarantees in order n d by epsilon time, where n is the number of points, d is the dimension, and epsilon is the accuracy parameter. What we end up showing is that we can get to an epsilon approximation in order n d by square root epsilon time, and using the same kind of smoothing techniques. So to look at the particular problem, the minimum enclosing ball problem can be formulated in this simple way, that you have this unknown radius that you want to minimize, and you don't know the center of the ball as well. So these are your variables. And what you want to do is that the distance of every point from the center should be less than equal to the radius. So it's as simple as that. So if you want to minimize r over r square for all xi, you might as well write it down as over maximum over all the xi's over this term. And if you open that out, that actually looks like this. And this is a maximum over xi's belonging, so basically a number of xi's lying on a set. So you can equivalently replace it by a variable lying on a simplex, because the optimum of a variable on the simplex will actually lie at the corners. So you end up getting something like this. And you can clearly see that this is the sum of a strongly convex function and the exact dual formulation that I was talking about in the past. And now your dual variable actually lies in the simplex, which is again a closed space, a compact space. And once you have this formulation, you can basically smooth it out and throw Nesterov's accelerated gradient scheme at it. In particular, we used a variant of Nesterov's accelerated gradient scheme, which is called the excessive gap scheme for this problem, but it is pretty similar. And the corresponding dual function looks like this form. So note that the dual function is smooth over here. And in this case, the duality gap is again given by this quantity. And you can, basically the entire rates is basically obtained by how fast you are shrinking the strong convexity parameter to, not the strong convexity, sorry, the amount of strong convexity that you're adding to 0. So basically mu k is going to 0 at a quadratic rate over here. So that is giving you the rate of convergence. And over in this case, sigma is basically the strong convexity parameter of the strongly convex function that you're adding. Script d is the upper bound on that small d function. And L, you can just think of L as norm of A transpose. So these are the various parameters that come in. And the reason I kept all these parameters in the rate is that these parameters are important. If you don't smooth in a proper way, these parameters will throw in various dependence on the number of data points or the dimension or something like that, and will result in suboptimal rates. So it's important to optimize it very carefully so that you end up getting the best possible rates. And the reason I'm mentioning is that I'll give you an example for this.
What does prevent you from big sigma?
Bigger sigma than this, you mean?
Yeah. So you should gain by getting a larger sigma.
Yeah, but if you have such a d which has a very large convexity, strong convexity parameter, then this script d might increase as well. So we end up getting a bound on script d by sigma actually. And so depending upon, so basically I'll give you two examples to just illustrate this point. This small d function, which is a strongly convex function, is often referred to as Prox function in the literature. So depending upon what Prox function you use, you might get different kinds of rates. So of course, we want to add a strong convex function, but a strongly convex function actually, the definition of a strongly convex function depends on the domain that you're working on. So suppose so currently my domain is just the simplex, but suppose I endow the simplex with the L2 norm. In that case, the natural definition of a strongly convex function to add is the 2 norms squared. So suppose I had added the 2 norms distance from the central of the simplex. In that case, my script, the upper bound script d would have been sigma by 2, but this Lipschitz constant of the dual, that will actually now have a dependence on the maximum eigenvalue of the A transpose matrix. And in general, if your A is an n by d dimensional matrix, this thing can have a dependence on the number of data points. So in particular, the convergence bound that you will get will be dependent on this script L, which actually will have a dependence on n in the worst case. Whereas, if you actually endow this simplex with the L1 norm, and choose your Prox function as the entropy function, which is strongly convex with respect to the simplex. In that case, your script, basically the upper bound now incurs a logarithmic dependence on the number of data points. But the Lipschitz constant now becomes independent of the number of data points. So it is just upper bounded by the maximum ball of the individual data points. And in this case, basically, you end up getting just a logarithmic dependence on the number of data points, which gives us the order star 1 by square root epsilon rates of dependence. So this is exactly the bound that we get for our algorithm. So this will actually converge to epsilon accuracy in order 1 by square root epsilon time. So as I mentioned, the problem of minimum enclosing ball can actually be applied to various other problems. In particular, it can be applied to the problem of finding optimizing support vector machines. So in particular, this is the simple objective of support vector machines. You have the hinge loss plus a regularizer. So SVMs are often solved in the dual in existing literature. And what was done around 2005 and 2007 was people noticed that if you take the dual of the L2 SVM, where you are actually working with the hinge loss squared, the dual of that particular problem actually looks exactly as the dual of the minimum enclosing ball problem. So in that case, people actually use the previous algorithms that were existing for minimum enclosing ball, and they just used it to solve the SVM dual. And they noticed that it actually gives you very fast convergence in real life when you have large data sets. So I think at one point of time, core vector machines were the fastest SVM solvers in practice, so around 2007 or something. And they were previously using core set-based algorithms, so they were getting order 1 by epsilon rates of convergence. Whereas if you use our scheme and just plug it as a subroutine for optimizing this, you will end up getting order 1 by square root epsilon rates of convergence. And so that is for core vector machines. And so one thing that might be of discord is that what we are doing here corresponds to L2 SVM, so basically hinge loss squared. So it turns out that you can even solve standard SVM, so basically the L1 SVM, where you just have the hinge loss, and you can solve it using these Nesterov style smoothing. So what is obtained is that, just to give you some introduction, previous state-of-the-art batch solvers, so basically bundle methods also solve the L1 SVM optimization problem, and they give you order nd by lambda epsilon rates. You can also use stochastic methods like stochastic gradient descent or Pegasus to solve the L1 SVM problem, and they actually get independence of the number of data points, but they'll give you order d by lambda epsilon rates for convergence, theoretically. So what we did was we wrote down the L1 SVM objective as, again, a strongly convex function, and the hinge loss as the dual of a smooth function. Turns out that this function, the original function g, is as simple as, so g of alpha is just summation of alpha I. And if you take the dual of that, you end up getting this objective. And in this case, the transform A is basically the product of the y times x matrix, where x is just the data points stacked up in a matrix. And so basically, since your SVM can be written down in this formulation, you can just use Nesterov style smoothing and then use any of the accelerated gradient descent scheme or even proximal gradient descent scheme, which is another variant of Nesterov's methods, and they'll both give you order nd by square root epsilon rates of convergence. Yeah.
So if you want to get a generalization error of epsilon, then n needs to be chosen roughly something like 1 over epsilon squared or lambda over epsilon squared, something like that. You can do the analysis of what n needs to be, and then compute the running time that you need. And you can do the same for Pegasus and see what happens there. And that would be like the correct comparison of what is there.
So one of the reasons that we actually had this around 2009, but we had compared, in order to put this into perspective with Pegasus, what we did was we compared with the batch version of Pegasus, and we beat the batch version of Pegasus straight away. But then everybody was like, why are you comparing with the batch version of Pegasus? Pegasus is supposed to be an online algorithm. And our method is strictly a batch algorithm, so comparing it with the Pegasus algorithm, which chooses 1 point at every iteration, was like comparing apples and oranges. So this point that you made was exactly what we did after that. So it turns out that our method, like in terms of experiments, we are actually kind of at the same league as Pegasus. So I'll show you quite a few algorithms in the next slide that we compare it with. So these are a bunch of algorithms that we compared it with. So batch Pegasus is basically the red line that we have. So this is showing the the primal function versus the number of iterations that it required to converge. And so Pegasus is basically the red line and ours is the blue line. So we are significantly better than the badge version of Pegasus. But there is this algorithm liblinear, which you cannot even see over here. It is somewhere over here. So that is like that is way faster than anything else that that way faster than our method, way faster than any of the existing batch solvers that we tried to compare it with. And it basically uses something like an implicit method in the dual. So what it does is, so this is the liblinear algorithm by Satyakirti and Chijelin. What they do is basically they look at the dual and update one coordinate at a time in the dual. So basically they do a coordinate descent in the dual and make the corresponding updates in the primal. And turns out they are way faster than any of the other algorithms. But then our objective over here was to show that we actually get faster rates than all the existing standard 1 by epsilon algorithms that are existing in the literature. So yeah, so that is as far as this is concerned. And yeah, so these are some other algorithms, these are some other plots which are basically showing how fast the primal function decreases in terms of the time in the particular seconds. So one thing that should be noted is that our method over here is bounding the duality gap, whereas all the other algorithms that we compare here with, they are basically dual algorithms. So they'll give you a bound on d of alpha star minus d of alpha k, where alpha star is chosen according to some ground truth. And then they just take that alpha k and get a wk corresponding to that using the same formula that is true only at the optimum. So theoretically, there is no bound to say how far that wk is actually from w star. In experiments, they perform reasonably well, pretty well. So that is what is generally taken as ground truth. But our method actually is efficient that way, both theoretically as well as practically, because you're bounding the duality gap and the thing, the distance to the optimum is sandwiched over there. So, pretty close to my end of my talk. So some other applications where I actually applied these things is basically the problem of finding the minimum enclosing convex polytope, which is again a computational geometry problem. So basically the problem is that you have a set of points and you have been given a fixed polytope and you want to find what is the minimum magnification of the polytope that is required to enclose these points. Turns out this problem can also be applied to certain active learning problems. And it was actually used by Dan Roth in finding active learning algorithms for basically active learning SVM problems. And you can convert it into the convex polytope problem. And our methods can also be applied to other max margin based problems, in particular structured. If you look at structured SVMs, then our methods go through over there as well. And it goes through over the entire, basically calculating all the marginals and the submarginals can be done efficiently in our setting as well. And we end up getting better rates than the state of the art. The state of the art methods for structured SVMs are again order 1 by epsilon due to Michael Collins and some of his co-authors. So we beat that and get order 1 by square root epsilon rates. And there's a problem of finding polytope distance, which is basically look at two polytopes and find the distance between them. And that is also a place where we can apply our algorithms and get. So basically all of these algorithms previously had rates of order 1 by epsilon to get to epsilon close to optimum. We improve it, all of them, to get to order 1 by square root epsilon rates. Yeah, so in conclusion, what we showed was that we can get improved rates for various machine learning objectives via this this particular smoothing style that we have due to Nesterov. And it gives you, so the key message is that you need not necessarily use Nesterov's algorithm itself. The key thing that actually happens is the particular kind of smoothing that you want to use. So suppose you smooth an objective, you can throw any good solver at it after that, and you can get very good experimental convergence, in practice. And this is true for very large data sets as well. So it is often very relevant. So as part of future work, we want to see if these, can appropriate smoothing mimic the performance of second order methods, since we are already using LBFGS. So can we basically say that, okay, if we smooth in this particular way, we can actually just throw a second order solver and, not incur the cost of calculating the Hessian. So basically we get performance as good as a second order solver, but just by doing smoothing and then throwing something which is cheaper to calculate at every iteration. And another thing that we have not done, the another thing is basically applying the smoothing techniques to more complicated measures like ranking measures, NDCG, or precision at the rate of K, or even F1 score. So these smoothing methods that I talked about, currently we can do it efficiently only for ROC area and precision recall break-even point. Turns out you have to hand pick the smoothing technique for each of. There is no generic smoothing technique that will apply across the board. So for something as simple as as generic as F1 score, we don't have a smoothing technique that gives you better rates. So that is also a potential future work that is existing right now. Yeah, so that's the end of the talk. Any questions?
For your last experiment, you showed that we're the SVM so fast. So since you already
that's liblinear.
Oh, linear. Okay. Since you already smoothed object function, your batch, did you try LBFGS on that one?
We tried LBFGS on that. It was much faster than our algorithm. So this graph that I showed, the blue line, it is due to Nesterov's algorithm. It is not due to LBFGS. It comes closer to liblinear, but it's still, liblinear is still faster. But that is that is because the liblinear code that is available in the repository is a very heavily optimized code, probably. It uses a lot of caches and stuff like that, and it does. It has like a separate cache to do something and so on. I'm not exactly sure why liblinear is so fast. It says that the theoretical rate should be log 1.
Average stochastic gradient, just a plain volume.
So you just
implemented correctly, it goes faster than linear.
The average the stochastic.
Yes. Average stochastic gradient when it's convex.
According to John Price not here. After you smooth, you run the LBFGS. That
so, but then
are
you doing something different from Pegasus, or are you?
I don't waste my time in the projection step. I set the learning rates reasonably well. The initial learning rate has to be computed right. And you do averaging.
What's the power of the decay on the learning rate that you said?
The decay is the same. It's just the starting point.
I see.
But it has to be different.
Yeah, we did not compare with.
And you do averaging.
So for your LBFGS, how you set your mu here? It's still epsilon over d.
But you can
in this case it's not.
It's faster if you want by selecting the direction.
So I think it's square root epsilon.
Square root of epsilon over d.
So epsilon by square root. But that is just a conservative upper estimate. For experiments, we tried various different possible values of mu and chose for the settled for the best one. And so basically we would start with a mu is equal to epsilon by square root d and then take 10 times that, 10 square times that, and so on and so forth.
I think the reason why we set mu to be epsilon over d is that you want to prove the rate and the first order method. But when you apply in the LBFGS, I suspect that if you're starting from a larger mu and gradually increase that, may lead to
so basically, no, but there is a sweet spot. If you continuously keep increasing it, at some point of time, it becomes worse. So basically, I think it's an artifact of the epsilon that you want to go to, how close you want to go to the optimal solution as well. And it's not necessarily a well-defined thing. Like if you work with 500 points and you work with a particular epsilon, the mu that you need to set is often different from if you're working with 1 million points. So that is